please immediately pass it back to me. Okay. Fine. And make sure that it is moving. Check with your friend or immediate row or whatever. So, we were doing, I was here. Now, we did go over this thing, right? I didn't discuss that. But it seems like there is some ambiguity. Okay, so let me resolve that. Because one of the students came to me after the lecture. And yeah. So, it is, these things happen, okay? It happens more in data science, machine learning kind of domain. I would call that abuse of notation, right? So what does that mean? Well, fine, let me go over this thing quickly, okay, one more time, and then I'll tell you where things could be confusing. Right now, in these slides, it will not be that confusing, right? As it is on the uploaded slides. And slides keep on changing, right? So the slide that I had uploaded last time changed a little bit. You'll realize I added a few slides. So here, we want to find out how good is the, our discussion is about R. Okay, seems like this is discharged. Alright, that's the bad news. Yes, working now. Great. So, our discussion was about R, Pearson correlation coefficient R. So, yeah, we should use R everywhere, lowercase r, but here it is uppercase R, please treat it as lowercase r. So, we learned about R, right, how to compute that, and you should practice, right, still, what today is 11. In 2 weeks from now. Okay, we'll worry about that later. And I'll also be doing a review also, so you'll get some idea about how to prepare for quiz and all. But anyway, we should know how to compare these things, how to compute these things, learn about R, okay? So then we also discussed like, okay, fine, if we find R, then how can we make use of R squared? What do we have in R squared, right? So some of, we had interesting questions, we had interaction like, what I have in my slide is little technical, which says that R squared computes, let me go over that. Here, the interpretation, right? So this was sounding a little too technical, so let's go over that and then I provide a simple explanation of that. The square of the random of the sample correlation coefficient R squared estimates the fraction of variance in Y explained by X. It's simple linear regression that we have seen. Either you write this way or you convey the same idea you define. So in my simple words, what I'll say R squared gives an idea about how much predictive power do we have in the independent variable X for the dependent variable Y when we are doing simple linear regression. It could be as simple as that. And yeah, I have been telling you, let me make that clear. How to use LLM is a big discussion topic even for the instructors. While you're preparing for your quiz, for your exam, why not just simplify those definitions? The definition, if you find is too difficult from our lecture side, look for a simpler explanation. Okay, and double check with us, double check with me. Hopefully, what you'll get would be good as well. So you don't have to memorize the definition. But anyway, we learned about it. I provided the simpler explanation of what this R squared means. Now here, the reason why I'm going over this thing one more time is that I fixed something here which needs to be fixed on the uploaded slide. So if you are accessing this slide, yours might be slightly different from what I have here. So, you know, maybe if you look at your slides, right, if you have downloaded it from Brightspace or if you're working on the Brightspace, in the earlier version we had an R over here. Right, so if you read it like that, 1 minus R squared is equal to variance in R divided by variance in Y. These two R's are different. Okay, so that's the reason why what I did. Now I don't have R over here. What I have is an E. Now question arises, what is this E? E is the residual. E is the residual. Earlier, we were referring to this residual as an R. If you do that, then yeah, we will have this confusion. This is R, which R you are referring to? Are these same? No, they are different. Okay, so this R that you have here is the Pearson's correlation coefficient. And now this will make more sense. It simply says that, you know, we can find out the ratio of the variance in the residual. Let me write it residual one more time. The ratio of the variance in residual divided by variance in Y is 1 minus R squared. This could be an interesting, you know, or an important relation to remember. And numerical problems can be solved on the basis of that. And this we can understand from this picture as well, which I explained. And one thing I forgot to mention, which you can also realize if you look at it carefully. And yeah, I think I mentioned to you, the variance could be understood as how much spread the values are. Okay, visually you can compute the value. We know how to compute variance, but if you look at this thing over here, this value would kind of represent how the spread of this thing, the value of Y. Okay, spread of the value of Y. That's what we have in the denominator over here. We know, or we should know that the formula to compute that. What do we have here? Here, in fact, we have this variance. Okay, what is this variance? This is the variance of the residue. What is the residue? I remember some very interesting questions asked by the students, and we had some discussion as well. This residue means how off we are from the actual value. We know why, right? Look at this scatter plot. For every point, take any point over here. It's a point in 2 dimensions. We know X, we know Y, right? But what is this line doing? This line is approximating the relationship that we have between X and Y using simple linear regression. Okay, so that's the thing. And one interesting thing which I observed and later on got a confirmation as well. If you look at these two pictures, right, and take this, what I should say, the line that we have in the picture A, right, which has some slope, let's assume it is 45 degrees approximately. In picture B, you're just making that horizontal. It's the same thing. It's the kind of same thing for visualization's sake, right? If you do that, then what you get is this difference, okay? This thing over here is the residual for each point. We have gone over these things for each point, right? The reason why I'm going over it one more time is that a student after the lecture came to me, and I'm very happy when I look at the students, you know, taking the notes and all. This thing, right? It was a little confusing, like, okay, fine, you have R, then you do 88.44%. How did we get that? The answer is that this is the value that you're getting after doing the R square over here. 0.94. If you square it up, you get some value around this. Okay, so this value is derived from here. And yeah, if you want to find out the variance in E, you should have some idea about variance in Y. Then you will be able to come up to that value. Otherwise, what we can say, we can only find out the fraction on the right hand side, R, where we know R squared is 0.884. Subtract that from 1, so it will come out to be 0.16 something, if I correctly remember from the last time. Question? Yeah, go ahead.
So, is the equation 1 minus the correlation where it's the variance of the rule or the variance of...
You got it. Yes, the variance of R. Yeah. Okay. All right, and yeah, we had some discussion on that, on this thing also, right? And guys, it may happen. I met some of you students, and I was happy to know that some of you have taken a course which is mathematics for data science, right? If that's the case, probably you are much better prepared, and you have learned much more math that I'll be teaching you in this class. So the reason why I'm mentioning this thing is, sometimes, right, when we are saying statistical significance, that doesn't mean that this exact statistical significance definition that you have in your stat class, right? So let's see what we have over here. It says that I did ask you to check, right? Yeah. So when I'm asking, I'll be prepared. This time I didn't ask, okay? Now, what it says, it simply says that the statistical significance of a correlation depends on the sample size as well as R. Right? So here, we are using this term slightly loosely, I will say. It's not that statistical significance test and all. Just making a statement that yes, if we have to use R, right, for our experiment, then it will be dependent on not only the value R, but also on the sample size. Right? As an example, I have only 10 students and I take them some values, right? Say X and Y value, could be height and weight, found some R, very excited about it, right? R came out to be 0.9 and I had only 10 students. So here, the sample size is small. That's what we want to communicate. Ideally, we want a very good value of R, because R squared is important. We will ultimately compute R squared, and R squared will tell us how much information do we have in X for Y. Okay, R is important. At the same time, sample size is also important. So this picture that you're looking at here is kind of conveying us the idea that, you know, how this population size plays a role in the value of R. Okay, so as an example, let's assume that we have sample size 25 over here. Approximately, I will, draw a line here to find out the corresponding value for Pearson correlation coefficient. Let's assume that it came out to be 0.379. I'm just coming up with some value. So for 25 sample size A, this is 0.379. Then if you have high population size like 200, then it is equivalent to having some Pearson correlation coefficient in between 0.1 and 0.2. Okay, and now the question arises, where from we got this this picture. I have the picture resource for you at the bottom. You can go and explore that thing in more this thing in more detail. And let me pull a few more points that I have here. Add a few points actually, hope that will have. Now, what I was explaining that we have here, which says that even small correlation becomes significant at 0.05 level. So that's the P level. I had some question in the last class with large enough sample size, right? So That's what I explained. Even small correlation becomes significant with large enough sample size. Now, 0.05 is the p-value. Now question arises, what is p-value? Just wanted to mention it so that if you have some understanding of 0.05, which p-value 0.05, and you confuse, okay, how come we have it here? Just for your reference, right now I have these points. It says that p-value here depends on the value of r, like how strong is the correlation, and also the sample size, like how many samples do we have, okay? And now, let me complete this whole discussion and then I'll ask if you have any questions. In the last class, last time when I was preparing, I did ask this question, like when we are reporting R and we get the value of P, then how should we interpret that P? Okay, this kind of question could be a valid question in quiz, and I would consider that as a difficult question on the quiz, right? When you have computed the value of R, right, assume that it came out to be 0.95 and the P is 0.10, right? Let me see if any student can attempt. Question is like this, right? Let's assume that we had 250 students or 250 sample size. R came out to be 0.95, but P is 0.10. What does it mean? Let's see if you could guess. What is this P 0.10? We got the value of R, but for R, another value has been reported, which is P, which is 0.10. Is that a good news or a bad news? Right? I think it's good news, bad news. But you have to toss a coin, right? Yeah. Come on. If you have coin, toss a coin. You could just have to say it's a good news. If it states it's a bad news. Very good, yeah.
It's not good enough.
It's not good news. Why?
Because even if the correlation coefficient is strong, the p-value is greater than 0.05.
Okay. Very good. Right? Now can you explain to me how? What do these values mean? Very good, perfect. You'll get 10 out of 10 for this question, right? What is this 0.05? What is this 0.10? I'm saying 0.10. What does that indicate? Good. Yeah, in simple words, right? For a layman, we haven't discussed that yet, right? We haven't discussed that. We will discuss that later. But yeah, fine. You're correct. But what is it? Can we talk about some probability? Yeah. Okay, seems like you people have studied too much. Let me make it very, very simple and let me know if that helps or not. If I'm saying that R is 0.95 and P is 0.10, then it says that the probability of getting this 0.95 value of R for a 250 sample size randomly is 10%. How does that sound? Right? It's like, what is the probability of getting this randomly where you don't have the real correlation? That's the thing, right? So what do we want? We want this probability to be very low, 5 or less than 5. Is that clear? That's what P means. Okay, and our cutoff is 0.05. Okay, so A in place of 0.10, it was 0.001. We'll be extremely happy because now we are saying that okay, we found this correlation 0.95 pretty high, and at the same time, my p-value is saying that the probability I would have got this result by some random thing, right, is just 1%. Okay, so I mean, if you want to go down to the real statistical significance and all, then we'll have to start with null hypothesis, right, and all those things. Okay, we will do that as and when the time comes. But for the timing, I believe we are good. Okay, question? All right, great. Now, guys, let's move on to another very interesting correlation coefficient, which is called Spearman rank correlation. A lot of interesting things can be asked, and I'll be asking some questions today, and let's see how it goes. So you are looking at some pictures, okay, and yeah, let's go over the pictures first, and then I'll show you the bullets that I have here. Okay, so what do we have in the picture? Comparison, okay? You have the data, picture 1, picture 2, picture 3. And for the data given to us, we have the value for Spearman coefficient, it's 1.0, Pearson correlation coefficient is 0.69. For the second data, Spearman is decent, Pearson is decent. In the third case, our Pearson is 0.57, but Spearman is 0.94, right? So scenario has been provided to you for pictures, and now on that data, these values have been computed. And let me see, now let me go over some points, and then I'll invite you for any questions if you have, otherwise I'll be asking you questions. So, how is this thing computed, right? I will be providing you the formula, and I have the data as well. So hopefully the data will help us in understanding how this Spearman rank is computed. Why do we call it Spearman and the other one Pearson? Very simple question, I won't be asking that, it's that simple. Do you know? Yeah. Nail it, here you go, right? And now the second slightly difficult question. Which coefficient came earlier? You know, who's the older gentleman? Pearson and Spearman. I won't be asking their date of birth and these kind of questions, right? Yeah. Any guess? Pearson, Spearman, you have your computer as well, but don't look there. It was Pearson first and then Spearman. That's what I remember, okay? 1800, I forgot the date because I looked at that in the last class. But anyway, okay, so how is this computed? For computing the Spearman rank correlation, we count the number of disordered pair, right? So what do we mean by disordered pair? And see, this is important, guys, so pay attention to this concept. In the Spearman rank, we count the number of disordered pairs, not how well the data fits the line, right? If you understood this point, then yeah, you can explain the first picture, right? What do we have in the first picture? In the first picture, well, Pearson is not that good as a Spearman. Why? Simple one-line explanation. Don't waste time on this, just less than 10 seconds it should take for you to even write, okay? In this picture, why do we have why do we have better value of Spearman's compared to Pearson? What do we do in Pearson? Pearson correlation coefficient, yeah? Perfect, right? We try to fit a line through the data, right? Simple linear regression line and all. Therefore, see the line, right? The best line that we could get is over here. This is the line, right? This is the line we got. And look at the data. The data, I mean, probably that's the best line you could get. And if you think about, you know, the residue and all, anyway. This is not doing a great job in representing the data. Therefore, Pearson coefficient is lower, 0.69, whereas Spearman correlation coefficient is perfect, 1.0. How did we get to that? We will learn that very, very soon. But interesting thing that you should notice in the data is a property, right? Does anyone know what property this data is following? In slide number 1. Do I have all the attendance? Anybody who did not sign? Everybody signed? Right? Guys, let's take a break, okay? I would need 3 volunteers. Will you be one? I may be wrong, right? Just count the number of signatures or IDs. Count signature and IDs. And third person, if you don't mind, can you count how many students are present? 5 minutes break, okay? Just 5 minutes.
What are you playing? Play hard cycle with my but it's not yeah, 15 hard.
You said 46?
I start over the hard with it. It's just the hard.
We have 4 extra.
Okay, anyway, yeah. Back to this lecture, okay? When I counted the signature in my first class, it was coming around 100 times, 100 hour. And I'm not sure 100 students are. It's much better than the last time, much better than the last time. Okay, last time I had 140 students and just 10 of it were showing up. It's much better, okay? Great, so, fine. Yeah, do you see any property in this data? That's fine if you don't know. Right? Increasing, fine, right? Seems to be increasing, but we have a better word that is technical. Sorry? And there's a word actually. Monotonicity. Monotonicity, okay? Reason is that in place of writing a paragraph, write a word, okay? Monotonicity. Okay, what does so? The question will arise very soon, may come in your exam also, like, what's the difference between these two? Pearson versus Spearman. I mean, you should double check, right? In my excitement, sometimes I give you the incorrect answer also. Spearman checks the monotonicity of the data, whereas the Pearson checks the linear fit in the data, right? How well can we fit a line there? That's the difference, okay? So here, in the first picture, if you look at, we haven't done a great job in fitting the line. But if you look at the monotonicity, right? I mean, every point if you see, right, is kind of following the ordered pair, right? This thing that we have. If we end up counting it, if you apply that formula that I'm about to give you, you will find this value as 1.0. So what is happening here? In simple words, right? It is up to you. You can use simple words also. We will learn about Occam's razor, okay? But it is a little early right now. As the value of x is increasing, y is increasing as well. That's what we need. X increases, y increases. Okay? So that is the case for every data points in the picture 1. But despite that, we could not fit a perfect line through it. You see that? Right? So, depends on what we want to find. Okay? Now in the second case, see, here, the data is monotonically increasing. We have a good monotonicity, and also we could fit a line as well. That's the reason both the values, if you look at Spearman as well as Pearson coefficients are giving the same value. How about the third one? Here, because of this guy over here, which we may call it outlier later on or even now, that's messing up with our Pearson correlation coefficient, right? Because of this much of, we could not explain this point, right? So maybe for that reason, our Pearson coefficient is not that good. We could get the perfect one, or better line, okay? Let's move on. So, we are kind of getting the motivation only for Spearman. Very soon we'll have an example and the formula as well. Thus, better Spearman is better with non-linear relationship and outliers, right? So yeah, someone or maybe myself could ask you this question, like when will you prefer Spearman over Pearson? You have the answer over here, right? Where your interest is to, again, please search it up, right? Monotonicity thing. When you want to identify monotonicity, and when you don't have the linear relationship, when you have outliers, you all can mention. And the exams will be paper based. Feel free to draw some plots and okay, great. Any question from me? Yeah, go ahead.
So, number one looks like a piecewise function, right? So,
Yes.
this has nothing to do with the Spearman coefficient. It has nothing to do with that. It's just that it could be not piecewise. It's just increasing all the time.
Yeah. Just increasing on, right? Okay. We have some data also. We'll have some interesting discussion on that. I added few slides from the last time. So here we go. How do we compute that? So for that, you have to compute the rank. So let the rank of xi be the rank position of xi in the sorted data from 1 to n. Okay, so yeah, I forgot to check that. Only you can remind me. Don't make your life difficult, right? Okay. Best rank means what? If I have 100 students in my class, what would be the best rank? 100 or 1? It's a very simple question, right? If you're proud about your rank in, say, high school, so will you be happy when it is closer to 1, or you'll be happy when it is closer to 200, 300? 1, right? So that's what I'm saying, ranking. Let's rank it from 1 to 2, 3, 4, and the lower is a better rank. That's the convention. Now, question could be, what will happen if we do the ranking otherwise? We'll have to figure it out, right? We'll have to figure it out. Maybe I'll come up with that answer next time. We'll keep our life simple. Ranking would go from 1 to n. That's what the slide is saying. Let's stick to that. Okay? That will be a notorious question to ask. Yeah, but we should be prepared for that question if somebody is asking. Okay, so for every data point, rank them from 1 to n. So in my class, if the quiz result is out, those students, yeah, that's again a tricky question. What will happen if, okay, let me let me give you the example. The quiz grades are out, maybe say 1 month from now, because in 2 weeks from now you have quiz, and then we have what rank for. Say somebody got 20 out of 20. There's only one student who got 20 out of 20. That will be rank 1, right? Then 19.5, 2, 3. So we'll have to compute the rank first, rank of xi. Now the question is, how do we compute this, right? The symbol for the spearmint is rho. You compute that in this manner. That's a little tricky formula to remember. We'll worry about remembering later. Let's first try to understand what we have here. So you will compute this as 1 minus 6 times di squared, summation of di squared, divided by n multiplied by n squared minus 1. Now question arises, how are we computing di? What is this di here? Now, you know, it's correlation thing again. We need two variables, right? We need two variables, let's call it xi and another one as yi, right? So we should have yi as well. So that you would find here, right here. How do we compute di? You need di here in this formulation. We have two variables x and y, one column with x value, another column with y value. So for each you will compute the rank and then you will find the difference. Let's look at an example. Here we go. Okay, so we are given some data. Let's assume 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 students and their score in English and Math. These are two exams, that two courses that they are taking. We have their grade. Okay. Now, simple. What you do, find the rank. Okay, shouldn't take much time. Yeah, making this slide takes a little longer. Understanding should not take that much time. So here, let's do that for English. The highest value is 80. We'll give that the rank of 1. Then second, I'm doing reverse engineering. It's rank 2, so I just make sure that this is the second highest number, 76, right? So you just eyeball, you will be able to figure it out that we have correct ranking. So this will be the rank that you're giving for English. It will be, where is my pen? Okay. These are xi values, and here you'll get yi values, right? Rank for y as well. Now, seems like this guy is really, really smart. This person scored first rank in Math as well, and then we have similarly ranking for other students as well. Now, once you have these ranks, xi and yi values, you compute the difference. Seems like it is the modulus of that. Whether you take modulus or not, you are anyway squaring it up. So the sign will not matter that much. Good, you get the value for d square. And once you have the value of d square, you can fit that in the expression. You sum it up. The sum of d square is coming out to be 54. We'll put that in the value over here. For rho, this is 1 minus 6 times 54 divided by, n is 10 for us. You do all the computation and you get the value for, what is it? Rho. Good? Question? If I ask this question, right, I'll give you 20 minutes, no problem. I will not give you calculator. It's okay, do it. The reason being, there is a fun that people of my age would realize, you may not realize, doing hand calculation. Okay, it doesn't matter whether you got the precise answer or not. The message is, when you're working on this problem, right, most probably, I'll give you homework. Homework should be out very soon, most probably this weekend. I would expect you to do hand calculation, okay, to boost your confidence, enjoy this thing. Anyway, good, right? Now tell me, for this data which is given to you, do you think Spearmint is the best that we are doing? Yeah? Or Pearson could be better? Or how do you decide which one is better? Is your question clear? Right? Again, very good, right? I'll give you first priority to answer. My question again is, you got this value of Spearmint, which is 0.67. Is this the best? That's one approach. That's one approach, okay? Then, okay, fine, you know, I got 0.67, doesn't look good. Let me try what? Pearson. Probably with Pearson, I'll get a better value. So if I'm getting better value with Pearson, I'll say, okay, Pearson, I'll use Pearson. Right? Spearmint or Pearson? Or we can't say. Yeah.
It depends on the data set.
It depends on the data set.
There's a lot of outliers and want to use Spearmint.
Very good. I didn't think of that answer. Very good. Right? So you understand what he's saying? But you know, yeah, for any general data where we have the probability of outliers, you will go with the Spearmint you are saying, right? Very good, good, makes sense. See, in data science, unless the question is direct, like what is the probability of this event, when we know the probability, the chances are pretty high that you may end up getting something greater than 0. Okay? Because questions are sometimes open-ended, right? Questions are open-ended. You can have, you know, more than one correct answer. His answer is correct, one of the correct answer, right? Any other answer? Is my question clear? You want to attempt? Yeah.
I think that Pearson was better
Pearson will be better. Why?
because the rank could be like very different based on only a couple points, but I don't think the data is so close to a lot of them, right? And then that can make it seem like the data is not really actually the two Pearson and
We are looking for correlation, that's what you're saying, right? And yeah, so you'll go with that idea that I had, right? Let's compute both the values. Whichever is higher, we'll report. Okay? Any guess, like will what is it? Pearson be better than Spearmint? Should do this exercise, right? Try this, but yeah, these are the things I added. Okay? So if you don't have the recent slides, then yeah, this is the slide that I added. Which one is better? Pearson 0.81, Spearmint 0.67, right? What does it say? Go with Pearson? Confused. When you're confused, that means yeah, you need to say something beyond the numbers, right? Yeah.
And the line is closer to the Spearmint.
Line is closer to the Spearmint. How can you say that?
Aren't the lower numbers the Spearmint numbers?
Pearson is upper, R is 0.81, Spearmint is 0.67. Those are some values that I have on the top to give you some idea of. Yeah, very good.
The numbers just say that since Pearson's is higher, dots are opposite.
Pearson is higher than. That's okay. Use simple English, right?
Compared to
Uh-huh.
over there, closer. But if Spearmint's is higher, then it would be.
What's your, you have to decide, right? You have to decide. You need to say something to your boss, right? So what will you say? You'll say, okay, fine. You know, the Pearson is higher. Yeah, I don't want to discuss about Spearmint. Okay? What would you say? Spearmint? No, Pearson? If you're confused, that's the good news. Yeah, next person.
This is saying it's Spearmint, like it's more accurate, like it's not like some of the values are on top of each other, so they're not really they're going in the same direction.
Uh-huh.
Some of the points are like kind of close to each other and on top of each other. It's not
Okay.
going one direction.
Let me tell you my take, right? Initially, I was assuming, right, that okay, if the Pearson is better, then I'll say, okay, we'll use Pearson. Guys, it depends on what we want to get from the data. How does this sound? It depends what we want to get from the data, right? If your goal is to find out, if your goal is to fit the line, which means if you want to find out by knowing the grade in English, how well can I predict the grade of a student in math, then go with Pearson, right? In the other case, if your interest is in the ranks, right? If your interest is in the ranks, then go with Spearman. That's my understanding, right? That's the reason I was saying, if you're confused, that's the better news, right? Because here, there's no perfect winner, according to me. According to me, there's no perfect winner. It depends on what we want to get from the data. Okay? Now let me change the problem slightly. Okay? If I give you the ranking of the student, let's say I'm taking 20 tests for you people. Okay? And then in those 20 tests, I only have rank of each student in every class. Right? What do you think? For the rank, should I use Pearson correlation? No. Right? For the rank, go with Spearman. With the rank, go with Spearman. Even better, depends on the nature of data. Right? If the data is ordinal, you need to understand what is ordinal data. I'll explain to you. When that data is ordinal, what will you use? Pearson or Spearman? That could be a quiz question. Okay? Use what? Spearman, Pearson. Spearman. Ordinal means the movie ranking, right? Movie being ranked 5 out of 5 star, 3 out of 5 star, right? So here doing math doesn't make much sense, okay? Your rank was 1 in math, your rank was 3 in English, so let me average it up. Your rank is 2. Does that make any sense? No. Right? I hope I'm giving up feedback, right? Questions? Alright guys, so why do I have these two pictures? With the rocket coordinates, the same, right? Oh, okay. How is this different? These are two different pictures, okay? How come? Look at the data, right? The data sets are different. What is this picture telling us? Pearson is 0.80, Spearman is 1.0. Does it say anything about the usefulness of Spearman over Pearson? Yep.
It seems like the data is only in 1 year past, so probably better to use Spearman.
Here you go, right? It's exponential, you can see that. Right? 1, 2, 4, 8, 16, 32. Right? Yeah. When it's not linear, you know that data is not linear, your interest is in monotonicity, guys, again, search for it, right? Then you go with speed. Good? Alright guys, so let's keep moving. Now we are moving to the other interesting thing, which is about correlation. We should be careful that correlation is important for us, but correlation does not result in causation. These two are different. Okay, so now it's on on your taste. I mean, if you love comics and all, read these things and let's see if you could understand. I'm not asking questions on these things, right? But the main message is correlation does not mean causation, right? Can we discuss about it, right? If you search it up, hopefully we'll get the same answer, because I also use the tool that you people use most of the time, okay? What does it mean? Correlation does not mean causation. Correlation, causation. Can we have an example where we have the correlation, but between x and y, but that doesn't mean x cause y or y cause x, or even vice versa. Okay? Yes.
So in season, specifically summer, ice cream sales go up, but
Yeah.
also people get bite by the shark also go up.
That's my favorite answer, right? And yeah, that's the reason I love, AI. But see, the example is so good. You understood what he's saying? If we have, what was it? The number of ice cream sales goes up with summer, right? That's what he's saying. And at the same time, what happens?
People get bite by the shark a lot more.
Sorry?
People get bite by shark a lot more.
Oh, shark biting. That's another interesting. Yeah, fine. Yeah, we can take that as well. So, does that mean eating ice cream results in biting by a shark? You see where we are going, right? So, causation, no, we cannot say that. But if we have one variable, probably that variable has some predictive power on the second variable. Okay, and we need to be very, very careful about this concept in data science. Okay, correlation does not mean causation. The example that I found was of ice cream and drowning. Right? That sounded very interesting to me. Eating a lot of ice cream doesn't mean that you will drown, but yes, it has to do with the third variable. You see where we are going? Causation may be in the third variable. You see? How about it? Let me use this thing. You found the correlation between x and y, right? But that doesn't mean x causes y or y causes x. There may be a z that is causing x as well as y, right? In our example, two similar examples that we had, which you can cite in exam, it's a perfect example, right? You can cite that in your interview also. The third hidden variable is the rising temperature. Okay, as the temperature rises, more ice cream consumption will happen, and people will go for swimming, shark bites, or drowning. Anyway, now the example that we have from our textbook goes over here. The number of police active in a person correlated strongly with the local crime rate, but the police do not cause the crime, right? So that's again an interesting observation. But in this case, the presence of the police the number of police present at a location correlates to the crime rate. Means that police does not cause the crime, fine, but it could be true the other way around, right? Like if you have a lot of crime, then yeah, most probably we have more police stations there. Okay? Guys, now this is a little interesting. I tried really, really hard to find some interesting example. Unfortunately, I could not. And I realized that this topic is little broader, right? So I may not be able to do justice to that, but I'll make sure that I explain what I have over here. But at the same time, I will invite some student to pick up a project in time series data analysis. Some of you have already picked some interesting data sets, right? I'm in touch with at least 5 students this time, which is pretty good, much better than last time. Yeah. Because with the time series data, you'll have their own interesting challenges, how to deal with all those things. But here, we will look at autocorrelation. Periodicity is a little tricky, but we will kind of address that. For really periodicity, seasonality and all, we'll have to go a little deeper. That will need at least one lecture on time series data analysis only. But let's see what we have over here. Autocorrelation. Till now, we have been looking at the correlation of two variables. Right? Two variables. The recent example, if you remember, your grade in math versus your grade in English. Two different variables for the same student, same set of students. We found the correlation. Autocorrelation is an interesting thing in time series where you correlate with the data itself. How does that sound? Correlating data with itself. Okay? Time series data, right? I hope you have an understanding of time series data. Let's come up with some data, okay? We discussed about it, and I know that you gave me a very interesting example of time series data. We will take one. Don't exactly remember, but yes, based on how we are feeling these days, let's assume that we are taking the temperature at 12 p.m. Just taking some time, okay? And say for the last, for 10 days, right, past 9 days, past 10 days, we had temperature like this. Just coming up with some numbers. 73, 78, it is in Fahrenheit, 75, and then 80, 81, 63, 1, 2, 3, 4, 5, 6, 72, 80, it could be any value, right? I need an example. And then 75 again, 1, 2, 3, 4, 5, 6, 7, 8, 9, one more, 69. That's the data given to you. Okay? Time series data, right? Because 1, 2, 3, 4, 5, 6, 7, 8, 10, I know that. 10. For 10 different days we have the temperature. You can visualize if we get the data for 365 days, 2 years, 3 years, right? Give us the data. We are data science people. We won't complain. Fine. If you take that data itself, okay, and compute its correlation with itself, autocorrelation with itself. You understand what I'm saying? Take this, correlate with the same data. What would be the value of correlation coefficient? Sorry, I forgot to mention this thing, and please, sometimes I forget, if you read my slides, right? What is the range of correlation coefficient value for Spearman? It is also in the range of -1 to 1. Okay, Pearson is -1 to 1, Spearman is -1 to 1. And I asked this question in the past, so please don't miss that thing. This point, right? It's very, very important. Spearman correlation is in fact the Pearson correlation of X and Y values in the rank. If you have the rank values and you compute, Pearson, then you'll get Spearman. Okay, we'll take that as it is, right? No proof, we are not doing proof enough. Important thing is that its value is in the range of -1 and 1, and also this point which says that in fact Pearson correlation of X and Y value rank is the same as Spearman correlation. After that we will conclude this point here. Okay, good. Yeah. Given the data, compute its correlation with itself. What will be the value? Correlate the data with itself. What's the correlation? It's a lot easier than what you people are thinking. Sorry? Yeah, come on.
Just ask, you can say the question again.
Yeah, this data, right? And then the same data again, okay? Finding out the correlation of the data with itself. Sorry, where is my pen? 73, 78, 75, 80, 81. Correlation of the data with itself. Yeah. It has to be one. Right? It has to be one. It's perfect, right? So when you are correlating the data with itself, it's one. Okay? It's that simple. So we are not getting any information by doing that. So when you do something like this, then the second series that I have, which I'm about to erase, will be called the same series with a lag of 0. Lag of 0 means we did not change anything in that data. It will get more interesting if I play with the series a little bit. What would be that? Playing simply means pushing the series a little bit. 73 here, 78 here, 75 here, and then 80 here, 63, 72, 80, 75, something like that. Push the series by one. Okay? Now, think about the intuition. What are we doing? Right? If you give me, say, for 11 days temperature, right? And I take the original 11 days temperature value, and then I start correlating that with its shifted value by 1 day, right? So, intuition wise, I am finding out the correlation between the 2 days temperature. Does that make sense? Right? Yesterday's temperature with today, I mean, if you go back 10 days, right? If you have these kind of values, right? You're finding out the correlation. It's kind of auto-correlation because the data is coming from the same time series. But what you do, you shift the time series a little bit by 1 day. You can do by 2 days also, by 3 days also, right? So in auto-correlation, what we do, we have this concept of lag, right? So what I am showing you right now is a lag of 1 day. You can introduce the lag of 2 days, 3 days, 4 days. Okay, so in autocorrelation, what is done for the same time series, we compute something called as autocorrelation function, and autocorrelation function gives us sometimes very interesting information which relates to the periodicity. How does that sound? Okay. That's the reason I was saying it is little difficult. So that's the reason I could not find very interesting problem to work on. How are we doing autocorrelation? Same time series, introducing a lag, and for every lag, for 1 day lag, 2 day lag, 3 day lag, compute the correlation. And for every lag, you'll have the value of correlation. Okay, and now plot that. Now tell me, if I get very high value of correlation after some lag of k, what does that indicate? Should I get that? If I do this exercise, should I get that, right? Or even before that, let me give you even better example. Right? We have a cinema hall, right? Stony Brook Cinema Hall, AMC, don't really remember the name of that place. If we get the time series data for the number of tickets sold, okay, every day, okay, and it's the time series data. You agree with me? Time series data, sale every day, right? And you do this autocorrelation kind of a thing, right? Are we expected to see some spike in the correlation after some lag? Now I'm asking you for intuition. If you have that intuition, then you'll understand, okay? When are the sale of the tickets expected to be higher? Right? Yeah.
If you had a lag of like a year, the correlation would probably
For which problem?
be
Lag of 1 year, very good, but which problem?
so the cinema.
Cinema, okay. Why 1 year for cinema?
Well,
What will happen after 1 year of movies?
movies probably have a specific time of what people are watching.
Okay.
With a certain mark. So
Okay. Good, I'll take that answer, right? I'll take that answer. But anyone who thinks differently, will we have to wait for 1 year? That's my point. That's my thinking, right? We are right, you are right as well. That's data science. Okay? That doesn't mean we will have any answer that will be correct. No. Answer should be reasonable enough. When should we expect the lag of 365 days? Which kind of data will show a higher correlation with the lag of 365 days? What repeats after 365 days? Temperature, yeah, that I can take. Sorry? Holidays, air tickets and all those things. So, get the intuition and then now think about this autocorrelation. What is it that we are trying to identify by computing autocorrelation? Okay, good. So, let me quickly finish these slides. Time series data often exhibits cycles which affect its interpretation. Now, the sale in different businesses may well have 7 days, 30 days, or 365 days lag. Now, when you have the time series, you can identify the cycle of length k, can be identified by unexpectedly large autocorrelation between the value of the time series at time t and the value of the same time series after t plus a. That's what the concept of lag is. Now, if you're interested in the formula for autocorrelation, here we have that. Alright, now one interesting thing about autocorrelation is that if the length is n, then you'll have to find out the autocorrelation for every lag, right? So which will be order of n. For bigger data set, this could be too much of work, but good news is that we have these techniques like FFT, fast Fourier transform, which can make it very fast for us. Now, to slightly simpler thing, right? But interesting at the same time, log. Log is very, very important, right? Probably you know what log is. We'll go over that and we'll see in what scenarios we will be using log for data science. So fine, we need, these are the basics, right? Everybody is supposed to know. If not, then please pay attention. Log is the inverse of exponential function. What does it mean? Well, if somebody gives us this relationship where y is b raised to the power x, so this thing that you're looking at, which I have taken, is the exponential function. Our base is b. Okay, so you can write y is f of x, right, is b to the power x. And it should be given to us that the base is b. Good? Now, the inverse function, right? Now we are not covering that much of math, but you are supposed to know, okay, that, well, if this relationship is given to us, if somebody is saying y is equal to b to the power x, now question arises, okay, fine, let's define x in terms of y. Well, for that you'll simply say x is log of y given base b. Alright, so these two things, basic math you are supposed to know. Why are we learning about that? You'll see that very soon. Now, we have no control over the data that we are getting. Okay, and we should not control. I mean, data should not mess up with the data. We can clean the data, remove the outliers, we can transform, all those things we can do. But yes, it is possible. You may come across the data which is exponential, like this one. Let's look at it. You can have a data, right, with these this pattern. Our b here in this example, b is 2, right? So it could be like 2, 4, then 8, 16. If you remember one of the plot that I had for Spearman. Now, the exponential data will look like this. Let's see what will happen if we do its log, right? So the corresponding log data would look like this, right? So the point is that the exponential grows really, really fast, whereas log grows slower. Okay, so for the same series, which is 2, 4, 8, 16, if you take its log, it will be 1, 2, 3, 4. You see, right? Now with log, we are dealing with these values, exponents. So now, where are we going? Exponential functions are associated with any process where we are repeatedly multiplying by some value b, okay, or we are repeatedly dividing by b. Is it that Is it really that complex? Can we come across a real life example where our data could be following the exponential distribution, exponential pattern? Can we think of? And these are the questions I ask. Right? Yeah. Good. Sorry? Standard deviation, right? Yeah, my confidence in biology is very, very low, but I can take that. Seems like yes, it should be a standard deviation, right? Okay, yeah, 1 to 2, 2 to 4, probably. That's exponential too, right? Yeah. Compounded interest, the way we compute, right? Yeah, right? Something that grows exponentially. The message is, it is common, right? Don't assume that you will not encounter exponential data. You will. Okay, any other example? Okay, so yeah, we did list few. When preparing, search for it, right? Search for more example. Come up with more interesting example in the exam. We are asking these questions. Okay, now this is something we need to remember. What do we need to remember? We need to remember this interesting relationship. What is it? It says that. And for that, do the math, and you'll have to probably do it. Okay, so it says that when we know that y is log of x base b, right, then b to the power y is x itself. Simple, simple. Do it, you realize, right? Maybe what is it? We are saying that, okay. I should leave it. If you're finding it difficult, then leave it. At least exercise this much, brainstorming. Remember, it's going to be useful for us. Good? Okay. Now, application of log. That's what we are learning. That's the reason why we are going over log one more time. You all know about it, right? So, logs are very important when we are dealing with ratio data. Right? Now search it up, like where will you encounter ratio data? That will be tricky, right? Like where will we encounter ratio data? But it's not difficult to realize that when you're doing some data analysis, it is possible that you may have a derived feature. Derived feature means a feature which was not originally there in your data, but for your analysis you use that as the value of two previous features, right? So in that it is possible that the new feature that you have could be the division of two previous features, the ratio. Okay, like old price, new price, it should make sense, okay? So the ratio is common. If you have the ratio data, then it's advisable that you use log. The ratio of two similar quantities, example new price and old price, they behave differently when they reflect increase versus decrease. This could be tricky, guys. It gave me tough time first time when I was reading it, and every time when I go to teach this, I make sure that I know what I have to say. So here we go, right? And we should be very careful about the terms that we are using here. Now when you have this ratio 200 by 100, let's assume that this is about the price, then this thing is called 200% above baseline, right? Here we are using the term above baseline. What you need to remember is that we are nowhere saying percentage increase. Percentage increase is different that we usually use in our day-to-day life. Percentage increase here would be 100%, but no, we are not saying percentage increase. When we are using this term, then here we just simply mean the ratio thing. So when the new price is 200, the old price was 100, then it is 200% above baseline. And if your price from $100 went down to $200, new is 100 but previous was 200, it is 50% below baseline. Now the issue is we are calling them similar because in one case it got doubled and the second case it got half. The ratio again, don't get lost in the words ratio thing, ratio. In one case it doubled, in the second it got half. So that is 200% plus and 50%, right? So in this kind of scenario, we should rather use log. That's the message. Why? Because see, if you do the log to the base 2, then when it is doubling, it will come out to be 1. When it is going half, it will come out to be -1. We need to do this. Log 2 base new price divided by old price. Now this will explain. When this was 2, your result was log 2 base 2, which is 1. And when it came out to be half, log 2 base 1 by 2, that is -1. And when it remains same, that will be log 2 base 1, that's 0. Right? So that's the message. Like when you are dealing with the ratios, go with log. Okay, in this case we are taking log to the base 2. Okay. Now, you need to remember these cases. I may not ask you to explain, right? Just remember these cases. When we're dealing with ratios, we use a log transform. And also, when we are dealing with probabilities, I should not have had this, but anyway. Now, one interesting thing about the probability is that the probability is a fractional value, right? The maximum could be 1 and the value is between 0 and 1. In scenarios like it's the naive Bayesian classifier, right? It's very common, very popular. We need to multiply probabilities, right? So even if it is 0.9, multiply that 3, 4, 5 times, you realize that it will go down and down and down. Okay, so the issue is that when we are dealing with the multiplication of probabilities, the chances are that the value will become so low that we will have to face the issue of numerical instability. So if we use probability, then we can solve that issue of numerical instability. I'll see you guys next time if you have questions.